Welcome back to the Deep Dive. If you've been following the automotive world over the last decade, I mean, the headlines have been just dominated by the electrification rate.
Well, absolutely. It's all about the 800-volt architectures, the 300-mile range battles, the luxury sedan price wars.
Exactly. But today, we are deliberately turning our attention away from that glamour segment.
We're focusing on where I think the true disruption and the real volume growth is happening, and
Yeah.
that's the micro low-speed electric vehicle, or LSEV market.
So we're talking about vehicles like the Wuling Hongguang Mini EV, or maybe the Citroën Ami in Europe,
That's the one, and this segment is maturing incredibly fast. It's moving from, let's call it a chaotic grassroots growth
where
phase.
they were using repurposed scooter parts, right?
Literally. Repurposed scooter or golf cart components. It's moving from that to demanding genuine, globally compliant vehicle-grade engineering. It's a whole new ballgame.
And our mission for you today is to step right into that new ballgame. We want you to take on the role of a chief systems engineer at a top global consultancy.
Mm-hmm.
You've just been hired to do one thing:
Yeah.
write the definitive, legally binding engineering requirements specification, the SOR, for a competitive electric drive system for these LSEVs.
And this isn't just a document, it's a detailed blueprint. It has to enable a global manufacturer to take this system from a blank sheet of paper through all the validation and into high-volume mass production from scratch.
Wow.
And this deep dive is really about understanding the high-stakes decisions that go into that SOR. The context here is it's brutal.
How so?
Well, for A or B class passenger cars, you have some margin for error. If a component is $10 too expensive, the profit takes a small hit, but the car is still viable.
Okay.
In LSEVs, if a component is $1 too expensive, the entire vehicle might be dead on arrival. It just won't sell.
So the core challenge.
The core challenge is solving what we call the impossible triangle of cost, performance, and compliance. We have to achieve, say, 100 km/h capability and global safety compliance, while hitting an unprecedentedly low bill of materials cost.
That sounds like a true engineering tightrope walk. You're balancing the regulations of, what, 3 different continents against the manufacturing simplicity of a utility vehicle?
It's the ultimate tightrope walk. And our analysis of the market and all the technical constraints, it already points us toward 2 non-negotiable strategic anchors, things we have to freeze into the SR immediately.
Okay, what are those anchors?
First, the system has to abandon the popular 48-volt low-voltage approach. It's a dead end for what we need. The voltage platform must migrate to a 96-volt to 144-volt high-voltage architecture.
Right.
It is the only way to deliver the power and efficiency we need without completely blowing up the cost of copper and cooling.
And the second anchor?
The physical structure. We must mandate the adoption of a 3-in-1 integrated e-axle
So that's combining the motor, the controller, and the reduction gear into one unit.
into a single, compact housing. Without that deep integration, we will never meet the required NVH, the packaging, and the cost targets all at the same time. These 2 decisions, they are the foundation our entire SOR is built upon.
Okay, so before we get into designing the system itself, we have to look at the rulebook. And I find this perspective we're taking fascinating.
Which is?
That the LSEV system design is, and I'm quoting here, inversely derived from regulatory limits, not from a desire for performance.
Precisely. You don't start by designing the fastest car you can and then see if it's legal.
No, you find the absolute legal limits and then you engineer right up to them, but not an inch over.
Exactly. You cannot define a globally competitive SOR without first mapping out all the constraints. So our initial focus has to be China.
Why China first?
It's not only the largest volume market by a huge margin, but it often sets the baseline for technical standards and safety expectations in this whole low-voltage sector.
Okay, so let's delve into that. The Chinese market, the GB standards, and what you call the safety baseline. Which specific standards are setting the floor for our engineering team here?
We are primarily concerned with 2 or 3, GBT 110488, which governs the motor system itself, and then the really crucial safety standards, GB 3A0331 and GB 183804.
And what is that first one, 18488, demand from us?
It provides an immediate and very high bar efficiency challenge. The SRR must specifically require that the overall electric drive system efficiency, and this is measured in its typical operating profile, must be greater than 88%.
88%. Now, that number might sound simple, but for a powertrain, especially one that has to be this cheap, that is rigorous. What does that efficiency target actually translate to in terms of, a real-world driving cycle?
Right. It's not about the efficiency at peak output. That's actually the easy part to achieve. It's about the efficiency under the CLTC, the China Light Duty Vehicle Test Cycle, which maps pretty closely onto typical city driving.
So stop and go, low-speed stuff.
Exactly. This means we have to optimize for the sweet spot of around 2,000 to 5,000 RPM and maybe 20 to 50 Newton meters of torque.
Which is where the car will live most of its life.
All of its life, practically. And since these LSEVs have tiny batteries, maybe 9 to 15 kilowatt hours, achieving that 88% efficiency in this core window is absolutely critical.
Because every percentage point you gain directly translates to range.
Directly to range,
Got
which
it.
is perceived value. Or you could look at it another way. It allows us to shrink the battery cost for the same range. So the motor design is instantly dictated by that efficiency map constraint.
Okay, let's pivot to safety, specifically the linkage required by GB 38031. You mentioned a mandatory response from the motor control unit if the battery pack has a problem.
Yes, and this is a vehicle-grade requirement that immediately separates our system from all the cheaper, non-compliant alternatives out there. GB 38031 governs battery safety, and if the battery management system, the BMS, detects an imminent thermal runaway,
Which is basically the battery catching fire.
it's an uncontrolled, accelerating heat reaction that leads to fire or explosion, yes. If that is detected, the MCU has a defined life-saving task to perform.
And what exactly must the MCU do in that scenario?
So because of this very tight no fire, no explosion safety window, the MCU must perform what's called an active discharge function.
Active discharge.
This means the power electronics have to actively pull the energy out of the DC bus, dropping the voltage below the safe threshold of 60 volts in under 5 seconds.
Wow. Think about that engineering challenge. Discharging a high-voltage capacitor bank safely and reliably in milliseconds.
It's huge. It requires millisecond-level redundant communication paths between the MCU and the BMS, and it requires specific hardware bypass circuits built right into the controller. These are non-negotiable cost additions, but they are absolutely essential for compliance.
That significantly raises the complexity of the MCU hardware and the software. It goes way beyond just turning a motor on and off.
It does.
What about the high-voltage interlock, or HVIL, from GB1T384?
HVIL is all about physical safety during maintenance or, in an accident. It makes sure that if any high voltage connector is open, say the main service disconnect, the system recognizes that break and de-energizes instantly.
And for a cost-sensitive LSEV, the engineering choice here is crucial.
It is. Do we opt for expensive, complex physical loops built into every single connector that short circuit when you pull them apart? Or do we rely solely on software monitoring of a current loop?
Given our extreme cost pressure, which way does our SRR lean on this?
See, the SR has to mandate a pragmatic approach. For the really critical points like the battery service disconnect, the physical short circuit loop is often the lowest risk, most reliable option.
Despite the marginal cost increase per connector.
Right. But for secondary harnesses, we would integrate software monitoring for redundancy. The mandate focuses on achieving robust, reliable HVIL across the whole system, but using the highest volume, lowest cost standard automotive connectors available. Not custom design high voltage units. The focus is always compliance achieved, cost minimized.
Okay, moving beyond China, let's look at Europe, the
Sure.
European market, and the L6E versus L7E categories, which you call the arbitrage opportunity. This is where Europe provides a critical loophole for our performance goals.
It really does. The European regulatory environment defined by these L-category vehicles is highly granular, and it's in that granularity that we find our competitive edge.
So you have L6E.
L6E, the light quadricycles, they're limited to 6 kilowatts of continuous power and a 45 kilometer per hour top speed. This is where you find the Citroën Ami, usually on a 48-volt system. They are city commuters, and that's all they can be.
And L7E is the category we have to target?
Yes. L7E, or heavy quadricycles, allows for a maximum net power of 15 kilowatts. This is the crucial performance threshold. But, and this is the core of our strategic decision, driven by ECE R85.
Yep.
This regulation distinguishes between net power and maximum 30 minutes power.
Okay, let's elaborate on that distinction. Why is that 30-minute power test so defining for our strategy?
The 30 minutes power rule is the continuous rating gateway for L7E classification. So our SOR strategy must exploit the definition of continuous versus peak. We will design the actual hardware, the motor, the controller's thermal mass, the reduction gear to be robust enough to deliver 30 kilowatts of instantaneous peak power.
A huge burst of power.
A massive burst. And it's necessary for that premium driving experience. We're talking rapid acceleration, safely merging onto slightly faster roads, overtaking a slow cyclist or a delivery vehicle.
So 30 kilowatts peak capability is baked right into the steel and copper. How do we stay compliant with the 15 kilowatt L7E limit?
We use intelligent software. The system's thermal logic and embedded limiters will constantly monitor the operating conditions. The software will ensure that the average power delivered over any continuous 30-minute period stays below that 15 kilowatt threshold.
So if the driver keeps hitting that 30 kilowatt peak over and over,
The software will initiate a gradual, managed thermal derating to protect the hardware and, most critically, to maintain the vehicle's legal compliance.
that is just profound. You're using a thermal test standard as a legal window to introduce a level of power that fundamentally changes the user experience. You're going from a basic slow commute to genuinely capable urban mobility, all without needing a different homologation.
It's the difference between a compliant vehicle and a competitive one.
It's turning a constraint to a market feature.
Absolutely. And on top of that, for Europe, we must satisfy ECER 100 safety requirements, specifically continuous monitoring of insulation resistance. The DC bus insulation resistance to the chassis has to be greater than 500 ohms per volt.
Which means more complexity in the MCU.
It mandates highly accurate, often redundant insulation resistance monitoring circuits integrated right into the MCU, which, yes, adds more complexity.
Okay, now to North America and Japan. Focusing on adaptability and packaging, the U.S. market brings a non-negotiable speed cap.
Correct. The U.S. FMVSS 500 regulation for low-speed vehicles, or LSVs, imposes a hard physical speed limit of 25 miles per hour. That's about 40 kilometers per hour.
And yet we've already decided our core hardware platform has to be 100 kilometer capable for global competitiveness. We can't afford to tool up two separate motors and controllers.
And that is the driving force behind our global platform strategy. The SOR has to dictate that this single high-speed hardware platform gets adapted via sophisticated software configuration.
How does that work?
We require a robust, multi-layered region configuration word stored securely within the MCU's memory. When the U.S. region code is detected, the software activates a specific PID control loop that effectively deadlocks the vehicle speed output at the 40-kilometer equivalent motor frequency.
The huge engineering challenge here has to be security and integrity, right?
Right.
The SRR needs to protect the manufacturer from liability if an end user tries to hack this limit.
Exactly. The SR must demand that this software limit is functionally secure and, frankly, non-crackable by the end user without authorized dealer-level tools. This means cryptographic signing of configuration files, monitoring software integrity at every boot up. We are shifting regulatory compliance from costly mechanical hardware constraints to scalable software integrity and security.
That's a massive saving in supply chain logistics alone. What about the demands of the Japanese market?
Japan, which is dominated by the key car or minicar segment, imposes really unique physical constraints. The big one is a maximum width limit of 1.48 meters.
So very narrow cars.
Very narrow. And for our electric drive system, this means the axial length, the front-to-back measurement of our integrated E-axle, becomes the primary packaging constraint. To fit, the SOR has to prioritize a compact axial length. This often steers motor technology toward solutions like concentrated windings.
Which is usually a cost-saving measure, but here it's actually a packaging necessity.
Precisely.
Okay, so let's summarize the global targets. We've navigated this regulatory minefield, and we've emerged with a single hardware mandate.
The SOR decision is locked in. 100 kilometer speed potential, 30 kilowatts peak power, built around a 96-volt nominal architecture. This platform is high capability by design, and then we adapt it via intelligent, secure software limits, whether that's the US 40-kilometer cap or the European 15-kilowatt continuous power cap, to achieve global compliance with one single bill of materials for the core powertrain.
Right. Stepping away from the regulations now, our next strategic hurdle is defining the system's architecture. How do we build the structure that delivers this performance while aggressively, and I mean aggressively, attacking the bill of materials cost? This starts with that foundational voltage decision.
It does. The voltage platform is the single most important variable defining the system's cost efficiency profile. We had to analyze the two major approaches out there, the Vallejo 48-volt systems versus the Wuling 96-volt plus systems.
Let's break that down then. The voltage platform showdown. 48V versus 96V plus circuits. Why is the 48-volt approach, which on the surface seems so cost-effective, fundamentally incapable of supporting our global L7E targets.
The initial appeal of 48 volts is really powerful because it falls below the 60-volt DC safety threshold. You bypass a huge chunk of the high-voltage safety compliance costs.
So no expensive orange harnesses, simpler connectors.
Exactly. No mandatory HVIL on every path, lower peripheral costs. But this is the lure of the 48-volt trap, and it's a trap based on ignoring some very basic electrical physics.
Which is a current requirement for a given power output.
Precisely. We need 30 kilowatts of peak power. If you use the simple equation P equals V times I at 48 volts, that 30 kilowatts requires a staggering current of over 625 amps.
625 amps.
And handling that much current brings two catastrophic cost penalties that completely doom the 48-volt solution for anything above, say, 6 kilowatts.
What are those penalties?
First, the sheer physical cost of the cabling. To safely and reliably carry 625 amps, you need extremely thick copper cables. We're talking 50 square millimeters cross-section or more.
Those are massive.
They're not only massive and prohibitively expensive, but they are physically a nightmare to route, bend, and integrate into the tight confines of an LSEV chassis.
And the second penalty is heat generation, which I assume pushes up the cooling budget.
You got it.
Yeah.
The energy loss, the heat waste, is governed by joule heating, or I squared R losses. Since I, the current, is squared in that equation, doubling the current quadruples the heat lost.
So at 625 amps, the losses are just exponential.
They are. The system becomes profoundly inefficient, it suffers from rapid thermal derating, and it needs an oversized, complex cooling system just to manage its own waste heat. A 48-volt system simply cannot sustain 30 kilowatt burst and remain competitive on range or cost. It is locked into the L6E category, period.
So the initial savings from avoiding HV compliance are just completely wiped out by the massive cost of copper, thermal materials, and all the inefficiency penalties.
It does. It fundamentally justifies our strategic direction. Our required solution is the 96 to 144 volt platform. At 96 volts nominal, that 30 kilowatt peak only demands around 300 amps.
Okay.
And that current level is the established sweet spot for high volume standard automotive power devices, whether we use high performance MOSFETs or standard IGBTs. It lets us use much thinner, cheaper cabling. It minimizes those I squared R losses, and critically, it supports the 100 kilometer at speeds and the 20% plus gradability we need for hill starts.
So the cost of the mandatory HV safety features is just a fraction of the savings you get back.
A small fraction. It's an easy trade-off.
So the voltage platform is secured. Now let's talk about the physical architecture. The mandatory 3-in-1 integration. Why does the SOR treat the integrated e-axle as absolutely non-negotiable?
For LSEV cost and complexity constraints, the traditional distributed system, where the MCU is in a separate box under the hood and long cables run to a motor on the axle, is functionally obsolete. The SOR has to mandate the 3-in-1 e-axle.
So what are the primary advantages of this deep integration?
The first major win is cost and EMC. Integrating the MCU directly onto the motor housing completely eliminates the need for those expensive, heavy, shielded three-phase AC power cables,
Which are notoriously expensive and noisy.
a huge source of electromagnetic compatibility noise. They radiate interference that can affect everything from the radio to critical sensors. Removing them simplifies the EMC compliance process immensely and just slashes the BM.
So you're solving a thermal, cost, and electrical problem all at once. What about refinement? NVH.
The second massive benefit is NVH noise, vibration, and harshness. By creating a single, rigid structural unit, you dramatically increase the stiffness of the entire powertrain.
Okay.
This increased rigidity shifts the system's natural resonant frequency out of the range of human hearing and away from the primary driving speed band. This is essential for elevating the LSEV experience from a noisy utility vehicle to a smooth, passenger car-like product.
And cooling.
Right. All the components can share the same cooling circuit, often even the same lubricating oil, which radically simplifies the plumbing and heat rejection.
Finally, let's define the cooling mandate in the SOR, passive water cooling. Now, given the intense cost scrutiny, why can't we just stick with the simplest solution, just air cooling?
Air cooling is the lowest initial cost, and for systems that are strictly limited to L6E power levels, say below 10 kilowatts, it's feasible. But the moment we introduce our 30 kilowatt peak power requirement, air cooling it fails.
It suffers from severe thermal derating.
Exactly. If a customer tries a 15 kilowatt sustained climb up a steep hill on a hot day, the air-cooled system rapidly overheats, and the software is forced to cut power to protect the hardware.
Which violates our ECE R85 promise, where we guarantee 15 kilowatts of continuous power for 30 minutes.
Precisely. Therefore, the SOR decision must mandate passive liquid cooling. This is a strategic choice designed specifically to pass that critical ECE R85 test at 15 kilowatt and to manage the heat from the 30 kilowatt acceleration bursts.
But how do you balance the cost of a liquid system with these budget constraints?
We engineer versatility into the hardware itself. The core 3-in-1 housing has to be cast with integrated water cooling interfaces.
I see.
So for the highest spec models, the ones sold in Europe, we activate the full liquid loop and connect it to a small radiator. But for the absolute lowest cost base models, we can leave those channels sealed and just rely on natural fin cooling.
But then you have to limit the performance.
Of course. The software will contain a permanent derating curve, limiting the continuous power to maybe 10 kilowatts. We build one hardware platform, but we can sell 3 different thermal capabilities based on software limits and whether or not we add a cheap external radiator. It maximizes flexibility and minimizes unique tooler costs.
Okay, so we're transitioning now from that high-level architecture to the really specific technical requirements. This is the section of the SOR that dictates materials, size, function. This is what our suppliers have to legally adhere to.
Starting with the e-motor specification itself. Why is the permanent magnet synchronous motor, the PMSM, the mandatory choice over, say, a simpler induction motor?
The mandate for PMSM is driven entirely by efficiency at part load. Induction motors do well at high speed, but LSEVs spend almost their entire life navigating city streets.
Low speed, high torque during starting, lots of time at part load. Exactly. PMSMs offer a fundamentally superior efficiency map in those critical operating regions. Given we're running on these tiny 9 to 15 kilowatt-hour battery packs, we cannot afford the 2 to 4% efficiency penalty that an induction motor would bring.
Because it just kills your range.
It kills range and it increases running costs for the user. It's a non-starter.
Let's get into the nitty-gritty, the non-negotiable performance parameters for the motor itself.
Okay. The motor has to be designed around a rated voltage of 96 volts DC, capable of operating reliably from 72 volts, which is a low battery, up to 115 volts, a high charging state. The performance targets are ambitious.
Go on.
Peak power is 30 kilowatts for a duration of 10 seconds. This is designed to achieve rapid acceleration, specifically targeting 0 to 50 kilometers per hour in under 5 seconds.
And continuous power.
The rated power, the continuous S1 duty cycle, is fixed at 15 kilowatts to satisfy ECE R85. We lock in a peak torque of 110 newton meters and a max speed of 9,000 RPM.
Now, 9,000 RPM is pretty fast for a primary drive motor. That suggests we need very efficient field weakening capability in the controller. But let's talk about the cost versus performance trade-off in the stator winding design. This is a classic choice in electrification.
It is. We face the hairpin versus round wire decision. Hairpin windings, which use rectangular flight wires, offer superior slot fill factor. More copper means 1 or 2% higher efficiency and better heat dissipation. They are technically superior, but the tooling and mold costs for hairpin production are massive and the lead times are long.
So given the LSEV cost focus, the choice is pretty clear. But let's articulate the strategic rationale.
The SRR must require round wire distributed winding. This is the highest value for money decision we can make. We consciously accept a marginal efficiency hit, maybe 0.5% below the theoretical max, to save significant upfront capital on tooling and to use widely available mature manufacturing processes.
That marginal efficiency loss is offset by battery cost savings. It's a necessary compromise.
It's the only way to hit the target bound cost.
Okay, now, on reliability. We are requiring a resolver over Hall sensors. What's the justification for that increased component cost?
Hall sensors are cheap and simple, but they suffer in accuracy and reliability when you expose them to the wide temperature swings, the vibrations, and the electromagnetic noise that are common in this integrated e-axle environment. A resolver is fundamentally a more robust electromechanical component.
And it gives you better control.
It provides superior control accuracy, which is essential for our high-speed 9,000 RPM operation and for the precision our FOC MTPA control algorithms need. We just cannot risk a field failure because of a sensor error. We also mandate insulation class H1 80 degrees C and IP67 protection against dust and water.
And addressing NVH. A common complaint about early, cheaper EVs is that motor whine and the low-speed shudder.
To mitigate that low-speed roughness, the SOR requires rotor-stator skewing.
So that's an oblique design.
The magnetic poles are twisted slightly along the axial length. This engineering detail dramatically mitigates cogging torque, which is that unwanted magnetic locking force you feel at very low speeds. It ensures the vehicle can execute a smooth, refined creep forward, eliminating the jerkiness that cheap, unskewed motors have.
Fulfilling our goal of vehicle-grade refinement. Okay, moving to the motor controller, the MCU. This is the brain, and the power devices have to be optimized for this 96-volt operation.
Right. Since we're at 96 volts nominal, the SR mandates the use of low-voltage, high-current MOSFETs, rated around 150 volts. This is a crucial device choice. Standard IGBTs are for 400 or 800 volt systems. At 96 volts, MOSFETs are just superior.
Why is that?
They offer significantly lower conduction losses, less energy wasted as heat, and a much faster switching speeds than IGBTs.
But the drawback is current capacity, as we said.
Correct. To handle the 300 amps of required current, we have to parallel multiple MOSFETs. And this arrangement necessitates using advanced cooling substrates like DBC direct bonded copper or IMS insulated metal substrates.
These are high-performance materials.
They're ceramics and metals specifically designed to pull heat rapidly and efficiently away from the silicon die, ensuring the power devices don't fail under those sustained 30 kilowatt peak loads.
And which specific control algorithms have to be baked into the firmware to hit our targets?
Mandatory implementation includes FOC, field-oriented control for precise torque and speed management, MTPA, maximum torque per ampere, which is vital for preserving battery range, and the critical field weakening algorithm.
That's what gets us to the high speeds.
Field weakening extends the motor's usable speed range past its base speed, allowing it to maintain constant power operation all the way up to 9,000 RPM. Without robust field weakening, the 100-kilometer target is just impossible.
Let's discuss the independent safety layer, the torque security requirement. How is this implemented and why is it so essential?
This is a direct response to functional safety requirements. The MCU have to contain a redundant processing core or logic that independently monitors the actual torque being produced by the motor.
Which it gets from the current sensors and the resolver.
Right. And it compares that against the torque being commanded by the driver's accelerator pedal.
And what are the failure criteria?
The SRR defines the critical threshold. If the deviation between commanded torque and actual measured torque is greater than 50 newton meters for more than 200 milliseconds, the system must initiate a hard, immediate, safe shutdown.
And this protects against catastrophic unintended acceleration.
Exactly. From a stuck throttle signal or a software fault. This logic is a non-negotiable part of defining a vehicle-grade system.
Okay, moving to the last piece of the 3-in-1, the reducer or transmission. How do we spec the gearbox for cost and longevity?
We mandate a single-speed, two-stage reduction unit, and we use helical gears because they offer superior noise characteristics compared to straight-cut gears. The primary challenge is defining the ratio.
Walk us through the gear ratio calculation that lands us in that 9-to-1 to 10-to-1 sweet spot.
It's a classic kinematic calculation. We know our max motor speed is 9,000 RPM. Our target top speed is 100 km/h. If we take a standard LSEV tire, say a 14570 R12, the rolling radius is about 0.25 meters. To achieve 100 km/h, that tire has to rotate at about 10 and 60 revolutions per minute. So the base ratio required is 9,000 RPM divided by a 1060 RPM, which gives us about 8.5 to 1.
So why go higher?
To ensure the motor can operate efficiently, and with margin utilizing field weakening effectively, a range of 9-to-1 to 10-to-1 provides the ideal balance between low-speed torque and high-speed efficiency. 9.5-to-1 is probably the final target ratio.
And what premium feature are we integrating into the reducer to elevate the LSEV from that utility vehicle feel?
We are moving away from the cheap, unreliable, cable-actuated handbrakes you find in basic models. The SOR requires the integration of a mechanical parking pawl, or park lock, driven by the shift-by-wire system.
This provides the tactile security and ease of use of a modern car.
It enhances the perception of quality and safety every single time the vehicle is parked. It's a critical NVH and customer experience upgrade that absolutely justifies its marginal cost.
In defining longevity.
The B10 life, the point where 10% of units are expected to fail, must be specified as greater than or equal to 150,000 kilometers or 10 years. This aligns with passenger car durability standards. We also have to demand optimization of the internal splash lubrication system, ensuring that churning loss is minimized at high speeds while still making sure every bearing gets lubricated at low speeds.
A small detail that directly impacts that critical 88% system efficiency target.
Every little bit counts.
An outstanding SOR is only the first step. The second, and arguably more costly step, is the test and verification plan. As engineers, we have to define the DVP&R, the design verification plan and report. For this integrated e-axle, what does the necessary torture look like?
The testing regime has to be brutal. Because this 3-in-1 e-axle is typically mounted low on the chassis, exposed directly to road spray, thermal extremes, and just severe vibration. We use the ISO 16654 standards as our template, but we heighten the severity to match the LSEV's use case.
Okay, let's look at the essential environmental and durability testing. What defines the extremes of our thermal and corrosion requirements?
The thermal shock test is critical for all the seals and material integrity. The unit has to transition rapidly from -40 Celsius to +85 Celsius.
So an extreme cold start to a hot underhood temperature after a climb.
Right. And the transition time between chambers has to be under 30 seconds for 100 cycles. This simulates rapid weather changes. We also mandate the damp heat cyclic test. 21 days of continuous exposure to 95% humidity, cycling between 25 and 55 degrees Celsius.
And the acceptance criterion here is crucial.
It is. The insulation resistance has to remain above 20 megaohms, validating that no moisture has gotten in and degraded the motor windings or controller substrates.
That seems like an impossible test for a cheap housing.
It forces the use of high-quality sealing technology. Then comes corrosion. The salt spray test must run for 720 hours.
30 full days.
Simulating years of exposure to road salt in coastal environments. We have to be sure the integrated aluminum housing won't corrode and fail. Finally, the IP protection test requires active submersion 1 meter deep for 30 minutes while the component is heated.
The heating is the key part there.
It is. It ensures that any small seal breach will draw water in due to the internal pressure drop, guaranteeing that our IP67 protection is robust enough for real-world conditions like floods or deep puddles.
Okay, moving to mechanical and performance reliability. The vibration test specifically highlights the architectural decision we made earlier.
The vibration testing is where we see the most significant departure from a standard passenger car powertrain. Because our 3-in-1 e-axle is rigidly mounted directly to the chassis structure or even the rear axle.
It could be part of the unsprung mass.
Potentially. So the level of shock and continuous vibration it sees is exponentially higher than if it were suspended on soft engine mounts in a protected cradle.
What's the typical passenger car vibration standard? And how does our requirement compare?
A standard engine or transmission might typically require verification at, say, 5 GRMs random vibration. Due to the direct mounting and the harsh LSEV environment, our SOR must require a heightened test intensity of 11 GRMs random vibration for 100 hours per axis.
11G. That is an extremely stringent endurance test.
It's designed to precipitate failure in the MOSFET power modules, the resolver connections, or the gear bearings if they are not robustly designed. It ensures vehicle-grade durability. We also require a 50-gram half-sign mechanical shock test to simulate hitting a huge pothole at speed.
And the regulatory performance tests are paramount for the final compliance sign-off.
Absolutely. The mandatory tests are defined by our strategy. The 30-minute continuous power test must be conducted at full load, generating the full 15 kilowatts in a controlled 25 degrees Celsius environmental chamber.
And this is the legal and engineering proof that our cooling system can sustain the L7E limit without derating.
Failure here means the vehicle cannot be sold as an L7E in Europe. It's a pass-fail gateway.
What about the torture tests that verify the motor's internal structure?
We require 2 key torture tests. First, the locked rotor test. This simulates a driver applying full power at 0 RPM like being stalled on a steep hill. The motor has to sustain maximum current until the software intervenes. This verifies the thermal capacity of the copper windings.
And the second one?
The overspeed test. Running the motor at 1.2 times maximum speed, that's 10,800 RPM for 2 minutes. This is purely to verify the structural integrity of the rotor stack against centrifugal forces, ensuring the magnets won't disintegrate under extreme overloads.
And rounding out verification, what are the EMC requirements?
We have to meet CISPR 25 Class 3 or ECE R10. The primary concern is conducted emissions, especially in the 150 kHz to 30 MHz range. This noise travels back into the vehicle's low-voltage bus and can disrupt radios, Bluetooth, or other systems.
The 3-in-1 unit helps, but it doesn't solve it completely.
Right. It minimizes radiated emissions, but robust filtering must be designed into the MCU's input stage to control that conducted noise.
Finally, competitive benchmarking.
Yeah.
We leverage existing market intelligence to validate our SOR.
And the market has already proven our concept, which is very reassuring. The Wuling-Hongguang Mini EV is the undisputed cost benchmark. It uses a 96 to 115 volt PMSM platform, validating our voltage choice, and achieves 20 to 30 kilowatts peak power, validating our performance targets.
So what's the strategic insight we take from them?
We learn their ethos of de-redundancy, their ability to strip out non-essential complexity to hit aggressive cost points. While our SOR mandates much higher safety standards for global compliance, we have to internalize their lean cost structure.
And the 48-volt alternative.
The Citroën Ami, with its Valeo 48-volt system, is the perfect L6E benchmark. Its 6 kilowatt max power and 45 kilometer R-speed constraint perfectly illustrate why 48 volts is only suitable for the entry-level, severely power-limited segment. It has zero upgrade potential for our global L7E targets.
What about a direct L7E competitor?
The Microlino 2.0 provides the most valuable comparative data. It offers 19 kilowatts peak power and a 90 kilometer ride top speed, so it successfully navigates the L7E category. Its existence validates our fundamental strategy. Using a high-efficiency PMSM in a tightly packaged e-axle is the correct approach.
Okay, the specs are frozen, the test plan's defined. How do we execute this? This SOR needs to be handed off to suppliers. What's our core supply chain strategy?
We have to adopt what I call the white box control, gray box hardware strategy. As the consultancy defining the SOR, we need to protect our intellectual property while leveraging the high-volume manufacturing capabilities of Tier 1 suppliers.
Explain that strategy and the ownership boundaries for us.
The white box development covers everything proprietary. Our control algorithms, the complex torque security logic, the thermal derating strategy for the 30-minute test, and that crucial regional configuration software for the US speed limit. This is the value add we own and develop internally.
And the gray box part.
The gray box purchasing involves acquiring the physical motor stacks, power modules, gear blanks, and housing castings from mature suppliers. We dictate the form factor, the material grade, the interfaces, everything in the SOR, but we utilize the supplier's standard high-volume tooling and assembly lines to minimize our initial capital expenditure and accelerate time to market.
That significantly mitigates our financial risk.
Yeah.
Okay, so who do we actually call to build this? Who are the strategic partners capable of delivering a 96-volt, 30-kilowatt, 11-dread capable system?
We have to look internationally. While established European Tier 1s like MAL offer extremely high functional safety systems, they often come at a cost premium that's unsuitable for LSEVs. Valeo is only considered for that niche 48-volt variant. Our primary focus has to be on the high-volume incumbents from China.
Like who?
Like Founder Motor, Shuanglin, and crucially, Inovance.
Why does Inovance stand out for this specific platform?
Inovance, particularly their LS32 platform, is widely proven in commercial and microcar applications. They already demonstrate the ability to meet extremely high anti-vibration standards, which aligns perfectly with our stringent 11-gram requirement. They offer the necessary blend of proven reliability, high throughput, and the cost-effectiveness we need to scale in the 96-volt market. They're the most promising candidate to issue this SOR to.
Okay, finally, let's wrap this analysis with a timeline. The 18-month implementation roadmap. This dictates our execution discipline.
Phase 1, that's month 02, is the SOR freeze. This is where our work culminates. We lock the specifications, 96 volts, 30 kilowatts, 3-in-1, and issue the legally finalized SOR document to the selected suppliers. No more changes are permitted after this.
Then we start testing components.
Phase 2, months 3 to 6, is the A-sample stage. We get initial off-the-shelf samples to validate our white box algorithms.
Yeah.
We do essential bench testing, mapping the efficiency, verifying thermal models before we commit to any custom tooling.
And phase 3.
Phase 3, months 7 to 12, is the B-sample and DVP stage. This is the first time we see the custom integrated housing with our specific mounting points. We initiate that massive environmental and durability testing defined in our DVP&R, the 11-dram vibration, the 720-hour salt spray.
And the final path to production readiness.
That's phase 4, months 13 to 18, the C-sample and product validation stage. We now receive samples built using production tooling. We complete the final vehicle calibration, including extreme winter and summer testing, and verify system integration across all vehicle variants, confirming launch readiness before that 18-month deadline. So, in a final synthesis, the success of this LSEV electric drive system, it's entirely secured by our strategic targeting of the regulatory and cost overlaps. By rejecting that limited 48-volt approach and mandating the higher efficiency 96-volt architecture and the integrated 3-in-1 e-axle, we've engineered a single platform.
A platform that meets high-performance targets while remaining globally competitive and fully compliant.
And it's all adaptable via software for everything from the restrictive US 40-kilometer cap to the performance-sensitive European 15-kilowatt continuous limit.
This detailed engineering requirement specification is now the comprehensive and legally binding contract that defines the entire engineering and procurement effort. It's ready to launch a vehicle-grade micro-EV platform that will redefine the LSEV segment globally.
And we built this entire SOR around legally exploiting that ECE R85 maximum 30 minutes power rule, designing for 30 kilowatts peak, but software limiting the sustained output to 15. Now that you understand how thermal monitoring dictates compliance, consider this final provocative thought for yourself. How might a future competitor use advanced telemetry and predictive algorithms, maybe combining GPS geolocation, known road grades, and specific driver throttle inputs, to legally push the perceived performance boundary even further, ensuring that 30-minute threshold is never technically breached in normal real-world use, thereby maximizing that premium feel without ever risking regulatory failure or increasing a single piece of hardware cost? That combination of control software, connectivity, and regulatory knowledge, that is the next frontier of LSEV strategic engineering.